Hello, Rouse. For lesson 2.8, let's take a different run at example 1. We'll use our general point approach, and then I've got another example for you also using a general point approach. It's a pretty useful approach to try out. So example 1 said the tangent to this cubic when x is equal to 0 touches the curve at another point. Find that point. So here's my rough sketch, and it's very rough. I mean, I've sketched what I think is a cubic. I've sketched a line tangent to there, and I'm trying to figure out where it touches another point. But my sketch is really just for organizational purposes here. Okay? So to try a general point approach, let's introduce a general point right here. And when you're doing this, it's probably a good idea to illustrate with a point that isn't actually the point that you're looking for. So I'm going to set P to be an element of F. That means that P is going to have coordinates something. I'm going to leave X to represent every value, and I'm going to let A represent some value. A comma A cubed minus 4A squared plus A minus 1. Right. Now, notice that, let's see, this right here is 0 comma F of 0. Notice that this point that I've chosen, the slope from here, let's call this Q, I suppose. The slope from Q to P is different than the slope at Q. So what I want to do is I want to make sure to find this point P, I want to make sure that the slope from P to Q is the same as the slope at Q, the value of the derivative at Q. So that's what I'm going to do. I'm going to set the slope of QP to be equal to f prime of 0. And I happen to know this value in this case. It's a little bit less general than our second example we did in class. Okay, I feel like I've got a bit of setup to do here, though. Let's get an expression for the derivative. Maybe I can backspace up here so that my reader can follow it a little bit easier. F prime of x is going to be 3x squared minus 8x plus 1. And now I feel like I'm ready to set things up, although f of 0 might be useful to substitute in. Let's say this is going to be 0 comma, it's a y-intercept. I think my reader should be able to figure out how I found that value. So for PQ here, I am going to use my old-fashioned slope formula, y2 minus y1. Let's see here, y2, there it is right there. A cubed minus 4a squared plus a minus 1 minus y1 all over x2 minus x1 is going to equal f prime of 0. F prime of 0 is going to be 1. The equation itself can look kind of complicated at this level, but we sort of trust that things are going to work out, and it gives us a decent way of approaching a number of questions, introducing some general point on here. This is a popular approach for optimization and even in vectors. So let's just do the rest of the question now. All we've got left is a little bit of algebra. We're going to have a cubed minus 4a squared. That's going to be plus a. My constant terms are going to eliminate. I'm going to multiply both sides by a. And then my linear terms are going to eliminate as well. I might have been worried about the cubic equation. I think this happened in class, that we're going to have to solve a cubic equation. Those concerns are alleviated when I factor efficiently. Solving by common factoring first. Notice we report both solutions to this equation. It's a cubic equation that it only has 2 solutions, because what we're really finding are the points of intersection here between this line and the curve. Well, there's only 2, right? And one of them is a double root, as a quadratic root. A equals 2 or a equals 4. Well, of course, a equals 0. Of course, a equals 0. That's the point of tangency that we were given. So I'm going to dismiss this. Make sure you mention it, but dismiss it, because it is not the point that I'm looking for. That's the point of tangency. Tangency. Okay. What was I asked to find? I was asked to find the point on the curve. So now I'll just tell my reader I'm evaluating f of 4, and that's going to be 4 cubed minus 4 times 4 squared. That's good. That means I won't need to worry about what 4 cubed is. Plus 4 minus 1, because this is 4 cubed minus 4 cubed, plus 4 minus 1 is 3. So we'll say the point, sorry about the space, is 4, comma 3, which is, yeah, the same answer that we got in class when we found the equation of the tangent line. But this might feel a little bit faster if you don't have to find the equation of the tangent line. Okay, give me a sec here to start up our next question, because it's not, I don't think it is, it might be on our newer versions of these lessons. Let's call this example 5 for this lesson. Let's show that a tangent line to f of x equals x cubed minus 3x plus 6 through q at -1, comma 4 will be horizontal. And I'm going to start with a sketch to try to organize my thoughts here. I'm going to have some sort of cubic. And this point right here, let me just double check and see it. I don't, in reading the question, I don't feel like it's on F. It's a tangent line to this curve passing through this point. It's possible that it's on there, but that would make the question quite a bit easier, I think. Let's see, -1 plus 3 plus 6. Yeah, that's definitely not -1 plus 3, 2 plus 6 is definitely not. Hang on. -1 plus 3 is 2 plus 6 is definitely not 4. Sorry. Yeah, so what we're looking at here is some point off of the curve, maybe like here. And we're trying to show that a line tangent to F through Q is going to be horizontal. Let's try a general point approach. Let's pick a point right here, P. Let's set P to be on F. Therefore, P is going to be given by something, comma, something cubed minus 3 times something plus 6. And then what we can do here is set the slope at this instant right here. The slope from P to Q is going to be the same as the slope of the tangent. Let's just discover when that happens and then convince our reader that the slope is actually 0 there. So once again, I'm going to set the slope from Q to P equal to the derivative of the function f prime of, I guess I'll have to call it a in this approach. Let's evaluate f prime of x for our reader so they can follow that relatively simple substitution. And then let's say QP. I'm going to do, I'll call this, I don't think it matters. I'm going to call this y2 and this y1. So y2 minus y1 all over x2 minus x1 should be equal to f prime of a. F prime of a is going to be 3a squared minus 3. I got a little bit more tidying up in this example. Let's try plus 2 equals, I'll do 3a squared minus 3, and then it's going to be multiplied by a plus 1. A cubed minus 3a plus 2 equals, let's try 3a cubed plus 3a squared minus 3a minus 3. And I think I'm going to subtract all of these terms from that side, leaving me with 2a cubed plus 3a squared minus 5 equals 0. Okay. Now I actually have to solve a cubic. Luckily, I think I can spot by inspection that a minus 1 is definitely going to be a factor. Notice that when a is equal to 1, 2 plus 3 minus 5 is equal to 0. So I'm just going to verify that with a little synthetic division here on the side, dividing by a minus 1 with coefficients of 2, 3, 0, and -5. Add, multiply, add, multiply, add, multiply, add. Yeah, we're going to get a minus 1 times 2a squared plus 5a plus 5 is equal to 0. I'm wondering if maybe this is reporting multiple solutions, but I don't know. These are all positive coefficients, and that c value is relatively large. Let me just calculate my discriminant here. My discriminant is going to be 5 squared minus 2 times, minus 4 times 2 times 5. That's going to be 25 minus 40, which is negative. Therefore, this part of my equation doesn't have any roots, doesn't yield any solutions. Therefore, the value of a is equal to 1. And what was it that we were trying to find? We were trying to find the point where... Oh, no, we figured out the point. Well, but we figured out the input where the line through -1, 4 is tangent to the curve f. Let's read what it is that we were asked to find. We were asked to show that it'll be horizontal. So all I need to evaluate here is f prime of 1. F prime of 1 is going to be 3 times 1 squared minus 3, which is going to be 0. Therefore, the tangent is horizontal. I wouldn't blame students for trying a different approach to this question to sort of visualize what it is that they've found, but the general point approach is a very useful approach. It's flexible. It can be used in some situations where it's not the most efficient approach, but if you're going to master one approach, you kind of want the most flexible one. So I would strongly recommend that you practice it.